Thank you very much. There will be no toric degenerations, but other degenerations. Other, yeah. First of all, maybe a few words about previous days. So what we did, we started with defining the classical objects. So we had the main guys are for us G, SLN, and we had irreducible representations. And we had flag varieties of lambda inside P of V lambda. So actually, this F lambda depends only on the support of lambda, not on lambda itself. So our basic object is Fn. So this is F rho, F omega 1 plus omega n minus 1. And so this sits inside the product of Grassmannians. So this is a very, very classical picture. Now we moved further to the, and so also one more point is that we have this Blücher algebra, Blücher lambda in general. So this Blücher algebra for lambda will be interested for Blücher n. So this is the homogeneous coordinate ring. And in particular, we had the Blücher n, which corresponds to this case. So this is direct sum over all lambda, V lambda stuff. Okay, and we had this semi-standard basis for this thing. So then we went further to the PBW version, Milen. And we've seen the V lambda A is a gr V lambda. So these are quotients of the induced PBW filtration on V lambda. And this Fs is just the span of F I1, J1, IR, JR, applied to V lambda, R being at most S. So this is our PBW filtration, and our space is the graded space with respect to this filtration. And we've seen some examples. So let me actually make those examples a bit more precise, a bit more concrete, actually. So the main example I'd like to actually describe now is the example of fundamental representation. So we've seen it, but let me kind of get back here. So we have here a vector V omega k, which is the high state vector, the product of Deutsch product of V1 Vk. And then what we know is that so if we apply F ij, which is nothing but E j plus 1 I. So this is the matrix unit which sends ith basis vector to the j plus first basis vector. Then, so if we apply this Fij to V1 Vk, so we are getting something new only if I is at most k and j is at least k, because so we want to take one of those vectors from 1 to k and move them to one of the vectors from k plus 1 to n. So it means that j plus 1 should be either k plus 1 up to n. And then what we get is V1 merge omitted Vk. Oh, sorry, omitted Vi. And up to Vk, and then adding Vj, actually plus minus, we don't care at the moment. So it depends on how many vectors are there to when we move it outside. But otherwise, it's just 0. And actually, so this is very classical, so this holds also in the classical settings. Now let us see what's going on when we are passing to the graded algebra. So we've seen that actually Fs modulo Fs plus 1 is identified with the span of those wedge products, Vi1 up to Vik, such that the number of elements in I, which are greater than k, so greater or equal than k plus 1, is at most s. Right, so we've seen that actually our operation, just what does it do? It sends some vector from here to a vector from outside of this initial segment. So if we want to take the quotient, so we just, sorry. So if we quotient Fs by Fs minus 1, so we say that we are moving exactly s numbers from this first part, from 1 to k, to the next part from k plus 1 to n. So there are exactly s elements which are greater than k. So this is our thing. And what is important that this implies that, let me write it as a remark, that the operators Fij such that I is greater than k or j is less than k act on V lambda A by 0. So you see, this is actually the main difference between the classical situation and this graded situation. So of course, this formula is true in the classical case as well. So there's no difference. So it's just how matrix units are applied to just this wedge product. However, this remark, of course, is not true in the classical situation. So we have all the possible matrix units, and they do act, right? So for example, so I'll give you an example in a minute, but of course, all Fij's, they act non-trivially in principle in V lambda A. So you can find a vector such that after you apply Fij to this vector, you're getting something non-trivial. However, in this quotient, the only remaining guys which do act, they are of this form. So let me show you an example, a very concrete one. So let n is 3 and lambda is just omega 1. So this is the simplest possible case is possible. So this is just, yeah. Sorry, so our lambda is omega. So this is this case. So let me do very even more concrete case. So n is 3 and lambda is omega 1. So this V lambda is just C3 with the basis V1, V2, V3. And then what do we know? We know that F0 is just a span of V0, V1. Then F1 is the span of V1, V2, V3. And nothing is left, so there are only 2 steps here, right? So we can make, starting from V1, we can send it to V2 or to V3, right? So there's no problem. But how do we do this? So we see that V2 is F11 applied to V1, right? So it takes the first basis vector sends to the second, and V3 is F12 applied to V1. Okay, so it sends the first vector to the third, but of course, as in the classical situation, F22, so this is a matrix unit F32, right? So F22 sends V1 to 0, so this is not the correct matrix units. However, what's important that in V omega 1A, F22 applied to V2 is 0. Okay, so this is not the case in the non-graded settings. So this is the matrix unit sending in principle V2 to the V3, but both V2 and V3, they appear at the F1, right? And we agreed on that, this Fij's, they have to be degree 1 operator. They want to send actually this V2 to the next step, but there is no next step, so this is 0. Okay, and so this is actually very minor but crucial thing, and maybe one more example is n equals 3, and lambda being omega 2. Then V lambda is lambda 2 of V omega 1, and this is span of V1, V2, V1, V3, V2, V3. And situation is very similar here, so the only kind of change, so is the symmetry between 1 and 2, so it means that F0 is the span of V1, 2. And then F1 is obtained as F0, and then plus we apply F22 to V1, V2. So this gives us V1, V3. So it changes V2 to V3. And plus F1, 2 applied to V1, V2. So it gives us V2, V3 up to minus. It changes 1 to 3. So we see that actually there is no room for F11, right? So in principle, from this vector to here, you can, from this vector to here, you can get by changing 1 to 2. But this is illegal because so this is already F1, and you should go to F2, and there is no F2. So F22 is 0 on V omega 2 F11. Okay, so this is somehow the way how you see the difference between the non-graded situation and the graded situation, and we will get back here in the geometric settings, but this is somehow important, and for the plan for today is, so we'll get back to the degenerate flag varieties, or PPW flag varieties. So we've introduced them yesterday, but we'll get back to the definition. So then we'll describe their some, of course, examples, and we'll give the explicit realization. And then we'll see that this thing has to do with quivers, with path algebras. We've seen them yesterday, actually. So we'll not need this complicated setup. We'll not need relations, but we'll need path algebras and representation theory. So we'll say something about quivers and representations, representation varieties. And finally, probably, maybe not today, but tomorrow, we'll go to the Quiver Grassmannians and well, link to what we discussed before. And flags. Okay, so this is the plan for today. So let me just first write again the definition of the varieties we are interested in. So these are F lambda A, which are defined in a very similar way to the classical thing. So you take n minus A and you apply it to V lambda, you close, and this lives inside projective space of V lambda A. Okay, so this is similar to the definition of the classical flag varieties. This is similar to the definition of the Schubert varieties. So in the classical flag varieties, we can have just a group G itself, so it's an orbit. For the Schubert varieties, we don't have such a group, so we anyway have to close. And this is what we do here. So a couple of remarks in order. So first of all, this group is very simple. It's not simple, but it is very simple. So it means that this is just exponent of the abelian Lie algebra. So meaning that it's also abelian, and this is the GA to n times n minus 1 over 2. So here GA is just the additive group of the field. And an element in this group is actually just an exponent of the sum Cij, Fij, ij from 1 to n minus 1. Okay, so all our Fij's, they compute now, right? So we don't care about the order. So you can write such an exponent in a very kind of natural and simple way. So just raise the operators to some powers. And theseCij's are just some complex numbers. This is an arbitrary element of algebra. Okay, so this is the first remark. And as a conclusion, we have that our FL lambda are so-called GA to the n varieties. So this n is, in our case, dimension of n minus a. So this is n minus 1 over 2. Okay, so what does it mean? So probably many of you are familiar with the toric varieties, where you have a torus acting on a variety with an open dense orbit. And the theory is very well developed and has combinatorial counterpart, algebraic, geometric, whatever. So it's very, very well known. However, here we replace the torus by another abelian group, which is GA to the power n. So, well, it's different, and there is no such nice theory for these varieties. However, there are many examples. And this is also an example of such a variety. And actually, we do know some examples from the classical theory. So one more remark, that classical Grassmannians are GA power varieties. So meaning that there is an action of the additive unipotent group, abelian, such a group, which acts with an open orbit. So of course, so let me give some details here. So of course we know that the group GLN or SLN acts on Grassmannian Kn. Well, and we saw these examples because this is a particular case of flag variety, right? So it acts within just one single orbit. However, there is a smaller group. Let me denote it by n minus k. So there is an abelian group which acts on Grassmannian KCN with an open dense orbit. And actually, this is very easy to write this group. So first of all, maybe let me start with the Lie algebra. So we have parabolic, maximal parabolic subalgebra, PK. So zeros here. Right, so this is the standard parabolic. Yep. Oh, no worries. Yeah. So you see, so what does this exponential mean? So it means that this is, this has to be an operator acting on some space. So you take 1 plus some Cij Fij plus 1 over 2 factorial sum Cij Fij squared plus so on. So it means that if we have operator Fij acting on some vector space, so we have this sum, this is also operator. Now we take such an operator and raise it to the second power. So we just think about operators acting on some vector space. So if we want to know how this group acts, right? Yeah. Yeah. Because if we take, so let's see how we multiply two elements here, okay? So we take some Cij Fij, and we multiply it by exponent some Cij bar tilde Fij. Okay, so this is one element of our group, and this is another, and this is just exponent of some Cij plus Cij tilde Fij, right? Because our operators, they commute, pairwise commute. So if we multiply two exponents, we just add up the coefficients. So these are exactly these numbers, right? So the coordinates, yeah. So the coordinates, this Cij, they exactly correspond to these coordinates here. So maybe more questions? Okay, so then let us get back to this parabolic group, and this is just the classical maximal parabolic corresponding to K. So this is K by K part. And of course, if we take Pk and apply it to V1 verge Vk, so we are just getting 0. Right, so, well, it can actually stabilize, so let me write, so we are not getting anything else, so it's in the span of V1 verge Vk. But let us consider the complement. So this is what is called abelian ideal here. So the complement is n minus k. So this is the set of our matrices where quite opposite, we have zeros here and whatever we want here. So we have here k, here n minus k. Okay. So this is our Lie algebra, and we can consider the corresponding group. So n minus k is the exponent of this group, of this Lie algebra. And actually the Grassmannian k b omega 1 is, we can apply this n minus k to v omega k, and then close. And this lives inside projective space of lambda k of v omega. Okay, so of course, we can do our general procedure, apply either the whole group or the whole low triangular subgroup, and then consider the variety. But it's enough here to apply only this part and then close. Well, one easily sees that because, so what do? We somehow take, say, V1, and we kind of produce some V1 plus something from here, and then V2 plus something from here. So actually, this is what is called the, without the closure, the orbit itself, V omega k is an open Schubert cell in the Grassmannian. Okay, so this Grassmannian Kn is an example of this GA variety, and actually we can get the following lemma from this observation, from this discussion, saying that the flag variety omega k A is isomorphic to the flag variety omega k classical, and this is nothing but the Grassmannian k C. Okay, so the lemma says that on the level of Grassmannians, we are not getting anything new, and actually the proof is more or less given already. The proof is that as modules over n minus k, the spaces V omega k and V omega ka are isomorphic. Okay, so what I'm saying that the difference between the graded and non-graded versions can be seen only on the level of operators which do not live in this additional part, so which are not in n minus k. So we saw that in the classical situation they act in some non-trivial way. However, in the graded situation, their action disappears. However, if you just think about this part, you don't see any difference. And so these are just isomorphic modules, and these guys are just isomorphic varieties. And of course, this group, which is seen here, this is GA to the power k times n minus k, right? So this is just the exponent of it. Okay. So this is boring so far, but let me give you the first non-trivial example to see that the things are actually much more interesting in general. The first non-trivial example shows up in the n equals 3 case. So n is 3, and then lambda is omega 1 plus omega 2. Okay? But so the question is how should we work with that? How can we understand what is this? So because in our definition, f lambda is defined as the n minus a closure of this highest weight vector inside the projective space of v lambda. And in general, these representations are quite complicated, so we were not able to do this. So in the classical case, of course, you can do this. So study these projective embeddings as well, but it's much simpler to embed flag varieties into the product of Grassmannians and then study these multi-projective embeddings instead of the just projective embeddings, because the spaces are kind of too large and hard to work with. So we would like to do similar thing here. So you remember one step back that we had the embedding v lambda plus mu sitting inside v lambda tensor v mu. So this is the Cartan embedding or highest weight component. And it's very easy to see that indeed v lambda plus mu is here, right? Because if you take the tensor product of two vectors, then it is a highest weight vector of weight lambda plus mu. So it's killed by the upper triangular part, and you have the weight, which we need. And then we generate something, right? So we send v lambda plus mu to v lambda tensor v mu. And then we just apply u of n minus to this v lambda plus mu to generate v lambda plus mu inside v lambda tensor v mu. So this is very classical, right? Now and you see this is classical, and this was very important for us because using this fact, algebraic fact, we were able to derive the corresponding geometric fact embedding. Yeah. Say it again. Thank you very much. Absolutely. Yeah. Thank you very much. Yeah. But here I'm getting back to the classical situation, but this is what we had in this case. So in order to somehow be able to work with the abelian version, with the degenerate version, we'd like to have something of this sort, right? But what is the difference? So we now let's look at v lambda a, and we see that this is u of n minus a applied to v lambda. Okay, so our now algebra is abelian, but still we apply all possible operators and we get the whole space. So of course this universal enveloping algebra is just a symmetric algebra, polynomial algebra, right? Because so they do compute the operators. So we can do a similar thing. So let us take V lambda A. Let us take V mu A. And inside we have a vector V lambda tensor V mu. So let me repeat that I'm using the same symbols V lambda and V mu to denote the images actually, right? So you remember that V lambda spans the 0th part of the filtration, so I'm not using the new notation, but it's actually not the same object, right? So then we can apply the universal enveloping algebra of n minus I, the symmetric algebra, to this tensor product, and ask what is it inside V lambda A tensor V mu. Okay, so now what we are doing, we are kind of playing the same game, taking the operators which are now commutative and apply it to this tensor product. Right? We don't have any high-state theory anymore, so we can't guarantee anything. However, the theorem, which is far from being obvious, says that this U of n minus A, V lambda tensor V mu, is actually isomorphic to V lambda plus mu A. Okay? So is isomorphic as U of n minus A mod. So I'm saying why I'm saying that this is a non-trivial theorem, because in the classical situation we have all the well-developed machinery of high-state representations, and actually after this machinery is developed, this statement is kind of obvious, right? So we know how do irreducible representations look like. We don't need anything. But here it's just some representation of the polynomial ring, right? And then you compare two representations. So one is defined from the Lie theory, and these two also. And then you have to compare, and it's not obvious at all that you have any connection, right? But this is the theorem. It's not known in general. It's known in types A and C, G2 as well, probably. But this is kind of the construction is very general, but no general statement is here. However, true in types and C. Okay. So based on this statement, we can get back to that example, and instead of working inside V lambda, we can work inside V omega 1 and V omega 2. Okay, so the conclusion, corollary is that F A lambda plus mu sits inside F lambda A times F mu A, where this line corresponding to lambda plus mu sent to V lambda times mu. And then the orbit, so for G in n minus A, G applied to this V lambda plus mu is mapped to G V lambda times G V mu. Okay. So this statement, this theorem, allows to kind of work with these simpler pieces. So in particular, so getting back to the example, we have that our F A omega 1 plus omega 2 sits inside F A omega 1 times F A omega 2. Okay, which is actually just Grassmannian 1 C3 times Grassmannian 2 C3. Any questions? Just the claim that the situation is kind of simpler. So let us just work explicitly, work out how it sits there. So this is part 2. So the question, what is the image of F(A) omega 1 plus omega 2? Right, so we have this variety sitting inside omega 1 plus omega F Grassmannians, the product of two Grassmannians. So we can ask how does it sit there? What pairs of points belong to this F? Okay. So in order to somehow understand how does the construction work, let us do very concrete computation. So we have G, which is exponent of C11 F11 plus C22 F22 plus C12 F12. Okay, so this is an arbitrary element from our group. And what do we want to do? We want to apply G to the product of lines. The first line is V1, and the next line is V1 verge. Okay, so this is just the general recipe. So just let's look what is the result. So both spaces are three-dimensional, so it should be something very concrete. So let's apply G to here. So what do we do? So G is of this form. So first of all, this exponent contains the identities. So we have V1. And then we need to apply the linear term, which is just this composition. So this guy produces V2 from V1. So we get C11 V2. This guy sends 2 to 3, so it doesn't do anything with V1. And this guy produces 3 from V1. So it's C12 V3. And the important thing that this is the end of the computation, but this is not the end in the classical situation, right? So in the classical situation, you also have the square of this operator. And in principle, you could send 1 to 2 and then 2 to 3. So in the classical situation, you would get one more term. So this would be C12 plus something like C11 times C22. But there's no such a term here. Okay. So this is our first part. And then we have to play the same game with the second factor. So we again have the identity operator, which produces V1 verge V2. So now we apply the linear term. So the linear C11 F11 wants to shift 1 to 2, cannot. Then this guy wants to shift 2 to 3, can do. So V1 verge V3. And then this guy sends 1 to 3, so it's also possible. So we're getting minus V to 3, minus C12 V to 3. And that's it. That's the end of the computation. So let me say again that this is different, this computation is different from the classical because we don't have these quadratic terms neither here nor here. Okay, so now the question is how these two things are related. So you remember this is a point in this Grassmannian, and this is a point in this Grassmannian. So this is a one-dimensional space, and this is a two-dimensional space, right? So it's clear what is the one-dimensional space, just a space spanned by this line. Now to make things explicit, let me actually write this as V1 plus C12 V3 verge V2 times C22 V3 plus. So let's check that I wrote it correctly. So we have the term V1 V2, and we have the term V1 V3 with the coefficient C22. And we have the term V3 V2 with the coefficient C12, and this is exactly this one. And this vanishes, so this is correct thing. So it means that this verge product corresponds to the span of these two vectors. So now the question is, so in general, in the classical situation, we would expect that this line has to lie inside this two-dimensional space, but we see clearly that it does not. But still, you see there is a connection, so this vector is very close to that one. The only thing that this kind of term, which we don't see there, right? So actually the conclusion is that if we drop this term, then we get what we want. So, so the conclusion. So this is so let me denote V1 to be the span of this first guy, V1 plus C11V2 plus C12V3, and then V2 to be the span of V1 plus C12V3, and then V2 plus C22V3. Okay, I just wrote the two vector spaces, one dimensional and one two-dimensional, corresponding to our computation. And then the claim is that we are used to the fact that V1 has to sit inside V2, but it does not. However, if we apply the projection operator sends V1 to V1, V2 to 0, and V3 to V3. It just forgets about the second coordinate. So then this is correct. Okay. So the element here is inside this two-dimensional space after we apply certain operator. Not itself, but after some transformation. Okay. So actually, now it is somehow reasonable to expect, and this is indeed true. So let me write it as a claim that Fa omega 1 plus omega 2 sits inside Grassmannian 1 C3 times Grassmannian 2 C3 and consists of pairs of spaces V1, V2. So V1 of dimension 1, V2 of dimension 2, such that projection 2 of V1 sits in V2. Okay. So you see, this is close to the classical picture. However, things become more interesting because we have this extra operator. Not really, because you see, if we erase both terms, then we are left with V1. Say it again. So you want just to erase this one? No, because we don't have such a vector. But you see, so this vector starts with V1, and this V2 plus C22 V3. But if this is V1 plus C12 V2, right? So it's different. So if I understood correctly, so you suggest to keep V1 plus C11 V2, right? But you see, so this vector is not present here. Because so if we want to write this guy as a linear combination of this and this, we need to, yeah. So this per 2 is just, it forgets about V2. So this is projection 2. The kernel is V2. And V1 and V3 are just preserved. So we apply to such a vector, we just erase this term and keep the remaining two alive. Okay? Yeah. Okay, so there's still something to prove, right? Because we show that actually in this open part, this is exactly the condition we want. But of course we close, so there is something to prove. But in this case, this can be done in a very easy way. So this is the claim. And in particular, so we see that if we believe, then we see that this variety, so corollary that the variety of pairs of subspaces V1, V2 with this condition, dimension of Vk is k, and projection 2 V1, 6 in V2 is of dimension 3. So which is n times n minus 1 over 2 for n equals 3. And irreducible. So because this is the closure of some open pairs, and in principle, if you're just given such a thing, okay, so in this case, it's not that complicated. However, you have to work to show that. So now let me state the general theorem, which with this example, I hope will be somehow, well, maybe not clear, but at least more natural. So the theorem says, yeah, yes, right, that's right. Mm-hmm. So in principle, of course, right. So in principle, okay, so maybe it's a good point. So let me add this as a remark. So remark. So the variety, the variety can be defined in a more kind of conceptual way as follows. So let us take, let f, phi, be a map from C3 to C3 such that rank of phi is 2. Okay, just let's take any linear map from C3 to C3 of rank 2. So then we're looking at, so then f a omega 1 plus omega 2 is isomorphic to the varieties pairs V1, V2 such that phi of V1 sits in V2. Okay, so V1 is one-dimensional, V2 is two-dimensional. In principle, you are absolutely right. So here we made some definitions. We fixed basis of V omega 1, V1, V2, V3, and therefore we are getting some very concrete realization. However, of course, whenever you have a map of rank 2, so you have a kernel, and this kernel is the projection. Actually, this remark will be important later, so this is somehow kind of base change for the Quiver representation. So we'll see that later. Okay, so one more remark actually that this variety f a omega 1 plus omega 2 is singular. So it's still three-dimensional, it's still irreducible, but it's no longer smooth. So we know that flag varieties are smooth. However, this guy is not smooth. And so we can write it explicitly. So namely, we have this Fa omega 1 plus omega 2 sitting in the product of Grassmannians. But actually, both Grassmannians are isomorphic to P2. Right, so this is just P2 by definition, and this is a kind of dual P2. And we have coordinates here, delta 1, delta 2, delta 3, and then delta 1, 2, delta 1, 3, delta 2, 3. And we can ask how to write the ideal, how to write the relations, cutting out the variety inside the product of projective spaces. And actually, with such a description, it's very easy. So this F, A, omega 1 plus omega 2 is cut out inside P2 times P2 by a single relation. Saying that delta 1, delta 2, 3 plus delta 3, delta 1, 2 is 0. Okay, so we see actually it's here. So we have this, our deltas here are 1, C11, C12, and 1, C22, C1. So what are the relations between those? So if you take 1 here times C11 minus C12, sorry, 1 times minus C12, and then C12 times, so this is exactly the relation we have there. And again, this is very different from the flag varieties, or not very different, but different because in the flag variety case, you have this extra minus delta 2, delta 1, 3, which is missing here, and but this is what is going on. And then there is a singular point uh, 0, 1, 0 times 0, 1, 0. So it exactly corresponds to the missing term, right? And you can, well, many ways you can show that it's singular point, but one way from this explicit relation. So this is clearly, this point clearly satisfies these relations, this the only relation, and one easily sees that it's okay. So now let me formulate the general theorem. So maybe some questions about this concrete case. Okay, so if not, here is the theorem. So let us look at the Fna. So this is F omega 1 plus omega n minus 1a. So we know that it lives inside the product of Fa omega k, k from 1 to n minus 1. And this is nothing but the product k from 1 to n minus 1, Grassmannian k of Cn. Okay, so we've seen that if we have such a weight, we can decompose it into summons, and then each summand corresponds to the Grassmannian. So you can ask what is the image, how does it look like? And then, so the image consists of collections. V1, Vn minus 1. So dimension of Vk is k. So these are points in Grassmannians. So you see there is no embedding. So these are so far just arbitrary collection of vector spaces. And the relation is that projection k plus 1 of Vk sits in Vk plus 1, where projection k plus 1 applied to the vector Vi is delta I k plus 1. Oops. Okay, so let me write it as this is 0 if I is k plus 1. And this is Vi, I is not k. Okay, so instead of having one operator, which was projection 2, so we have now a bunch of operators. So k is from 1 to n minus 2. So we somehow connect. So the conditions are still local. So meaning that we compare Vk to Vk plus 1. But this comparison is not just embedding, as it used to be, but we have to apply some operator, right? So we should transform this Vk before saying that it belongs to Vk plus 1. Okay, so maybe let me draw the picture. To make this somehow statement a bit more clear, so let example. So if n is 3, so this is the example we studied there. So we have our map per 2, and let me just consider such a picture. So here I put vectors V1, V2, and V3. So I have two columns. The dots correspond to bases in my space. I have two spaces. And I pretend that V1 is a subspace in this three-dimensional space, and V2 is a subspace of this three-dimensional space, okay? And now what is our operator? So it's written in a very simple way. So V1 is mapped to V1, V3 is mapped to V3, and V2 is mapped to nowhere. Maybe let me add this nowhere here. So this red line is the difference between the classical situation and this EBW situation. I just erase this part. Now let me write a picture for n equals 4. Now I have to write 4 columns, 3 columns, each consisting of 4 vectors. So this is V1, V2, V3, 4. And now what are my maps? So here I have a projection. This is projection 2. Here I have projection 2 and projection 3. And projection 2 sends V2 to 0, here like this, and here like this. And the difference between classical and non-classical thing are those 2 lines. So you see that just I pretend that V1 sits in here, V2 sits in here, and V3 sits in here. Okay, so I take some one-dimensional space here, I map it using this per2 map, and then it should sit in V2, and then it should sit in C, and this is the answer. Okay, so in particular, the theorem implies that, so in particular, this explicitly defined subvariety inside the product of Grassmannians, K from 1 to n minus 1, is irreducible and of dimension n times n minus 1 over 2. Right, because so we saw that from the definition that n minus, so our flag variety f lambda is defined as the closure of the orbit of v lambda. So therefore, in order to understand the dimension, one needs to answer what's the dimension of this open part. And clearly, this is the dimension of effective subgroup, which acts here. And if lambda has the full support, if this is somehow omega 1 up to omega n minus 1, there's no stabilizer here. So this is indeed of the same dimension as the flag variety. But from this definition, it's far from being clear. So this is somehow the outcome. Okay, so of course, I do not have time to go to something else, but let me maybe just say a few words. What are we going to do tomorrow? So for those familiar with the representation theory of quivers, so representations of quivers. So the 2 maps we had there, so the map, the collection, so the flag varieties, classical flag varieties. And these EBW degenerate flag varieties. They somehow correspond to different representations of the equioriented type A quiver. So in order to somehow understand this correspondence deeper, and in order to be able to work with that, to develop it, and to understand what we have behind, so we need somehow some more details on the quiver representations, and this is what we're going to do. Thank you very much.
Questions?
your question is what is the connection, or can we do the similar thing? Yeah. So let me give two answers. So the first answer is that yes. So in principle, all the definitions work for Schubert varieties as well. So Schubert varieties sits inside de Mazur module. So de Mazur module each de Mazur module is generated from the cyclic vector by the action of Borel. So you can also apply this procedure with the PBW filtration, and you can define these varieties. So the answer is that it's kind of in general, there is no general information. So there are some papers treating the PBW degenerate flag varieties, or Schubert varieties, or PBW degenerate de Mazur modules. So there are some papers by Gislan Fourier and some papers by Machlin, Igor. So there are some steps, but there are no general information, so the situation is kind of complicated. But the question is very interesting, and the construction works in a general setting as well. So this is the first part of the answer. And the second part of the answer that actually I didn't write it, but maybe I'll say it once again tomorrow, that these degenerate flag varieties, they turned out to be isomorphic to a Schubert variety for a larger group. So this is a kind of coincidence, and I don't have any conceptual explanation. But for SLN, you can take the group SL2N, and you can take some parabolic partial flag variety and some concrete W element of the group while group, and then this degenerate flag variety will be isomorphic to the Schubert variety for this.
Also, this theorem, you expect it to be true in all cases?
I don't have enough evidence, so it's kind of very tempting to conjecture, but I tried kind of during several years to prove it, but I failed, so I don't know. I don't have counterexamples, but I don't.
So you prove this theorem by determining the defining relations?
Yes. Yeah. So you just, the way to prove that, you show that, describe this via defining relations. You prove that this guy satisfies the desired relations, and then you show that the dimension is at least the dimension of V lambda plus. This is the way. But in general, we don't have kind of.
So now, if we take 2 copies of SLN, and then like we can do this PBW filtration even for the tensor product, because they are irreducibles.
Say it again. So you want to
take SLN direct some SLN.
Very good. Yeah.
So then you do this procedure.
So you take the tensor product of 2 modules, and you take the tensor product of high-split vectors, right?
So then we would be able to define ablination of that, V lambda tensor V mu as SLN direct sum SLN ablination. Do you think like
it's a good point. I don't know.
V lambda A tensor V mu A, like
maybe, but I don't know.
Like classical picture.
I don't know.
Or rather,
so I have a quick question about this realization of the flag variety as the orbit closure. Do you know what happens to the other elements of the flag variety which strictly lie on the closure? I mean, they can be realized or seen as some sort of degeneration of V lambda. Does that come with a natural type of order?
No, but you mean, so we in this PBW flag varieties, we have an open orbit, right? Yes. So you mean points which are outside this open orbit, right?
Correct, exactly.
So there is so I mean, you see, this theorem gives us the description of the whole variety, yes, right? So you have this part which belongs to the open orbit, and you also have some kind of outer part, right? Some divisors, but you have this very explicit thing, so you can describe them explicitly. You can say what are they, how they, they have cell decompositions and so on. So in a sense, right? So I mean, you can find for each element in the closure, you can find kind of a path leading to that. But this theorem gives you kind of explicit description.
I see. I see. Thank you.
Yeah, I'm just generalizing Venkatesh's question. So, I guess you can ask this for G semi-simple, where the things are of type A.
Right. It's a very good
Yeah.
question, but
Yeah.
I don't know.
Okay.
Yeah, yeah, very good question. I never thought about that.
If not, let's thank Professor Feigin again. And
Okay.